According to Fourier's theorem, if we take any well-behaved periodic function, f of x, with period 2L, we can re-express the function as an infinite sum of trigonometric terms. The coefficients an, bn, and a0 are given by these formulas here. Since the cosine functions are symmetric in the y-axis, when we add up a bunch of cosine terms, the resulting function is also symmetric in the y-axis. We call these functions even, because they could also be expressed as a polynomial with only even powers of x. The baseline term here controls the mean signal level. The factor of a half here is included only so that the formula for an is general and includes the a0 case. The sine functions have rotational symmetry about the origin, and this property is retained when we add up the sine terms. Functions of this type are called odd because they could also be expressed as a polynomial with only odd powers of x. In a separate video, we looked at the square wave, drawn here. The function alternates between 1 and -1, and I've drawn it here with period 2L. We discussed an application of square waves in cathode ray tubes, and it was also shown that the square wave function can be represented by a decomposition of this type. Because the square wave has rotational symmetry about the origin, all of the an coefficients are 0, and in this case it turns out that the bn coefficients alternate between 4 over n pi and 0 for odd and even values of n. In the cathode ray tube, at the same time as the voltage signal controlling the electron beam intensity is delivered, the beam needs to undergo a side-to-side deflection called a linear sweep. The electron beam is taken across the screen from one edge to the other, and then is returned back very rapidly when the beam reaches the other edge. A current like the one shown here can be applied to the magnetic coils controlling the movement to achieve the required behaviour. This function is called a sawtooth wave. It's the periodic extension of the function f of x equals x on the interval from -L to L. Let's calculate the Fourier series expansion of the sawtooth wave. Like the square wave, it's rotationally symmetric, and so it can be expressed using only a sum of sine components. We can calculate the coefficients bn using the given formula. We can integrate this function by parts for the case when n is not 0. For integer values of n, this term goes away completely, and cos n pi can be replaced by -1 to the n. So, the final result for the coefficients is given here. The case when n equals 0 needs to be considered separately, but this coefficient turns out to be 0. We could also have inferred the fact that the constant term is equal to 0 from the graph, which shows that the function encloses equal areas above and below the axis. A plot of the first few terms in the series is shown here, and we can see the convergence to the sawtooth waveform in spite of the secondary oscillations.